All right, I'm going to see if I can tuck in a quick screencast here before the bell. I'm looking at one of the UBFPM example problems. And in this one, there are two blocks connected by a string. It's a low mass string, we'll ignore the mass. There's a pulley, it's a frictionless pulley. So basically, string and pulley, all they're doing is providing a path for the force to get from M1 to M2. So I've got a system schema set up here, M1, M2. There's a tension between them. And then M1 experiences a 40 Newton gravitational interaction because it's got a mass of 4 kilograms. And M2, it's touching the ramp, so there's smoosh push there. 90 Newtons gravitational interaction with the Earth. And then, of course, the tension with M1. So I can start to piece together my free body diagrams for M1. This is FG. And it's going to be 40 newtons, and there's also a tension force here. For M2, there's gravity here. This is 90 newtons. The tension, if you look at it, it's not going to be straight up. It's going to be at an angle. This angle from the surface is 42 degrees. So over here, if I make the horizontal, I don't know how well I've drawn that, but this is 42 degrees, and that's the tension force. And then I also need to have my smoosh push in here. And that's got to be 90 degrees to the surface. So if the tension is parallel to the surface, there's a 90-degree angle between the tension and the smoosh push. I don't know how much smoosh push. I just know that there is some because it's resting on the surface. What else do we have going on here? So it looks like M2 is going to slide down the angled surface. So it's going to be going like that. So that means M1 is going up. I'm going to go ahead and make a notation over here regarding the acceleration. So this thing's going to accelerate that way. This thing's going to accelerate that way in the direction opposite the tension, because the tension is up the ramp, the acceleration is down the ramp. And that kind of informs how my diagrams are going to go here when I decide to add these forces together. So I guess I don't really need to redraw it. For the acceleration to be up, that means that the FU has to be up here. And that means that the FU is going to have to point that direction over here. Acceleration and FU are the same direction. They just different magnitude and units and all that good stuff. All right. 40 newtons down. And tension up. Ooh, I didn't draw that long enough. The acceleration and the FU are going to be up. So that's a way to know that the tension is greater than the gravitational force. I'm going to move this down a little bit. There we go. All right, so, oh, come on, dude. So here's my FU here. And I can tell based on the arrows that FU here is going to be the difference between the tension force and the 40 newtons. If I hadn't mentioned it yet, since this is one line in the system schema, I know that this tension and this tension have to be the same. They're part of the same force pair, so I could draw a little triangle to go with that. But I don't know what the tension is, so I can't put that in yet. All right, with regard to this diagram then, I've got gravity down. My smoosh push has to come back up. So that if those were the only forces acting, I'd have an FU down the incline. And the acceleration would be down the incline. They are not identical because this is 90 degrees here. The leg and the hypotenuse of the triangle cannot have the same length. So clearly I know the smoosh poosh. Let's make that 2. Make gravity 3. Those are not the same length. Okay. We try to look at where the angles show up in here. So if this is 42 degrees there, then this is going to be 90 minus 42. So this also has to be 42 degrees. This is 90 newtons. So now I can just do a little bit of trig because that's the adjacent side to the 42 degrees. I can take the hypotenuse times the cosine of 42, and that's going to tell me what the smoosh poosh is here. And then I've also got this tension force. I don't know how much tension force, but I do know that it is not going to quite close the gap because I've got to have some FU pointing down this way. Got to have some FU down the incline. All right, excuse me just a second. All right. So back into this here. Punched it into the calculator, and 90 cos 42. This smoosh poosh here has to be about 67 newtons. And then over on this side, we're opposite the 42 degrees. So if I do 90 sine 42, I get that this side has to be 60. Somewhere in that ballpark, 60 newtons. Okay. Then when I look at the problem and think about the tension here, I know the tension has to be less than 40 newtons in order for this thing to accelerate upwards. So, okay, if the tension was 40 newtons, definitely I would end up with an FU pointing down the ramp. But as it stands, I don't know what this tension force is, and I don't know what the FU is. I know that I know that this side of the triangle has to combine to be 60 newtons. So I can figure out the FU pretty quick. I just need to think about the velocity versus time graph. And here we see this thing travels 1.4 meters in 4.5 seconds, and then it starts from rest. So the velocity versus time graph is going to start from rest. The area of it will have to be the 1.4 meters, and then the time here has to be the 4.5 seconds. We can use that to figure out what the acceleration is going to have to be, and ultimately that's going to let us know what's going on with the FU and kind of complete our triangle. So let's see, let's call that H. So 1.4 equals 1/2 the base times the height. I want to solve it out for that height. So I'm going to have 2.8, 2 times both sides there, divided by 4.5. And that's going to give me 0.62 seconds. Okay, so that's the change in the velocity that happens in 4.5 seconds. So I can find the acceleration. That's the change in velocity. This is meters per second. Help if I would have started out with units in there. Divided by 4.5 seconds. Not a very big acceleration. That's 0.14 meters per second squared. Okay, so I've got the acceleration for this object. It's going to be the acceleration for the other object as well. But now I can go in and I can find the FU for that block M2. It's got to be the mass of M2 times the acceleration of M2. I know the mass of it is 9 kilograms, and the acceleration is 0.14 meters per second squared. So 9 times 0.14, 1.26 newtons. So now I know a little something more about this now. If this FU is 1.26 newtons, and this arrow here has to be less than 40 newtons, there's got to be something else going on in here. Otherwise, we're not going to fill up this gap, okay? And so that's the thing that's kind of cluing me in, along with the fact that there's some mention in the problem about coefficient of friction, that there's another force that's acting along this axis. So I'm going to shrink that up. And can I get rid of that? Okay, shrink that up. So there's got to be another force in here, and that's going to have to be friction. So there must be some frictional force at play here as well. And it's acting that direction because that's going to help this diagram make sense of itself. The FU, the 1.26 newtons, the tension force here, and the friction have to be oriented like that for this diagram to make sense. So now if I look at this, I can write an algebraic expression for the FU over here. Well, no, I know the FU is 1.26. And I got to go cover another class quick, so I'm going to pause this. All right, where was I? So we just figured out the FU is 1.26 over here. That'll be the FU for that object to get an acceleration of 0.14 meters per second squared. It'll be a different FU over here. This FU for object 1 is going to be different. But they will have the same acceleration, 0.14 meters per second squared. So I can come right over here and say FU equals 4 kilograms times 0.14 meters per second squared. And where are we going to end up? .56 newtons is the FU. And that, of course, has to equal Ft minus 40 newtons on this one. So add 40 to both sides. 40.56 must equal the tension force. So that's exciting. Now I know the tension is 40.56. I'll just call it 40.6 newtons. Okay. That's close enough to government work. The accepted values over here. They're using 0.138 for the accelerations of both objects. They get 39.8 newtons of tension. I mean, it's basically 40 newtons of tension. Just got to be a little bit more, right? Gosh, how the heck would that even work? Oh, if they're using 9.8 newtons per kilogram times the 4 kilograms. They would have an FG of 39.2 instead of the 40 that we're using over here. So that's how they can get away with a tension force of less than 40, just being a little bit more precise with the values. But the physics is still kind of working out the same. We know we've got to have a tension force greater than the gravitational force. All right, so if that tension is 40.56, that means that over here, why did I think it had to be less than 40? That's not right. This has to be 40.6 newtons. All right, so this is 40.6 newtons. That's 1.26 newtons. This whole thing's got to be 60. So that tells me the friction force has to be, can we really embiggen this bigger? Let's see. 60 minus 1.26 minus 40.6 That's going to equal the frictional force.
She said stop her peeing.
Oh, hallway kids. So that's going to leave 18-ish newtons for the friction. And the last thing that we're asked to find is the coefficient of kinetic friction between M2 and the incline. Okay, well, FFK equals mu K times smoosh poosh. And we know that the friction force has to be 18.16 newtons. Sorry, let's call that 18.1. Come on, eraser. There we go. 18.1 newtons. I want to solve for mu K. The smoosh poosh we established earlier was 67 newtons. So 18.1 newtons point divided by 67 newtons equals mu K. Calculator. Oop. 0.27. No units because the newtons cancel out. This is the coefficient. How'd we do? Yeah, that's in the ballpark. There we go. All right. So that's how this problem is solved. A couple important ideas. If they're connected by a string, the tension in that string is going to be the same for both objects, at least as long as these strings are massless. That if I can know things about the motion, like it starts from rest, it covers this distance and this amount of time, I can piece together the velocity versus time graph, and the acceleration is going to be the change in velocity divided by the change in time, which is the slope on that graph. That's also going to be the same ratio as the FU over the mass. That's really the big thing in this unit. Then knowing things like thinking about the direction of the acceleration, so I can think about the direction of the FUs. Thinking about the direction of the friction to make sense in the diagram. That the smoosh poosh, because we're on an incline, it's going to be less than gravitation. I've got to use some trig to figure out this tricky triangle here. And it's about the size of it. So applying most of the tools from the model here. Good luck with the rest of it.